This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today, I'm really excited. We have a new faculty member here in HCI and related areas, and it's Ge Wang. And I met Ge when I heard about Ge long before several months before he got here. That the word on the street was that we had an exciting new person coming. And when Ge arrived, soon after he got here, we went out to dinner and had great conversations. And I'm particularly excited for this talk today because I haven't seen anything that he's going to talk about. In fact, I think trying to explain live interactive music performance over dinner is probably one of the harder things to do. And while Ge does it very well, I'm excited to see it live.
Thank you very much, Scott. And all right, so thank you all for coming. And so this talk is kind of broken up into two parts. The first part is about ChucK, a programming language for computer music. And a related second part is about designing instruments, most of that using ChucK, for laptop orchestras. I'm Ge Wang, and this is work done with many, many collaborators, wonderful collaborators at Princeton, Stanford, and elsewhere. So I have a big thank you list at the end. And we begin with two quotes, and you'll recognize both of these people, I think. First one says, "The old computing is about what computers can do, whereas the new computing is about what people can do." And that's from Ben Shneiderman. The second quote is from the great Alan Perlis, who says, "A programming language that doesn't change the way you think is not worth learning." And so in this first part of the talk about ChucK, we'll present our motivation. And indeed, it is our motivation in writing ChucK to change the way, or at least provide a different way of thinking about how we program music and audio and how we analyze that through code. So in particular, we're interested in exploring the programming the passage of time in a programming language. For example, to specify and control time at a flexible granularity, but also to kind of reason about time in the code that we've already written. In a similar vein, we also want to address the issue of concurrency, or how to actually program parallel flows of logic and to actually have them sync up together in a meaningful, precise, and with a flexible granularity. And a bigger goal is to really use this as a vehicle to gain insights about the audio programs that we ourselves write, and also about the programs that our colleagues and friends, students, and teachers write. And to make audio programming more accessible, and to further enable kind of this idea of rapid experimentation, both in exploring with sound making, music making, performance, and even audio analysis and information retrieval. So those are kind of our broad motivations in doing this. But we're certainly aren't the first. In fact, as far back as the 1800s, people have been writing about using computers to make music. So here we have Lady Lovelace working with Charles Babbage, and that's a difference engine. When she and Charles were working on the analytical engine, which was never built, but it's a more advanced version of the difference engine, she wrote that, supposing, for instance, that the fundamental relations of pitch sounds in the science of harmony and of musical composition were susceptible of such expression and adaptations, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. And this is from 1843. And indeed, as electronics and then computers came and became more prominent parts of our lives, we've indeed tried to make music with computers. And the earliest programming language efforts, specifically geared for making audio, is by Max Matthews, who we have the honor of actually being present. He's sitting right there, who made Music 1 back in the 50s and 60s, Music 2, 3, 4, and 5. There are many different versions of this because until Music 4, and please correct me if I'm wrong, this was all programmed in assembly language that was actually specific to the hardware it was running on. So every time there was a new update to like a machine, you had to actually write a new language, essentially, that's based on the new instruction set. But Music 4 actually is the first time that it was actually implemented in a portable language, it's Fortran. And then we have Music 10, Music 4B, Music 11, 3.6. These are all programming languages kind of derived from Music 4 and 5. And some of these are programmed by our own John Chowning, Wyndham at Princeton, C Sound by Barry Verco at MIT, C Music, Common Music, Common Lisp Music, both also Karma Lights, Eric Taubey and Bill Schottstead, C Mix by Paul Lansky at Princeton, Open Music, Formula, Nyquist by Roger Dannenberg at CMU. The list goes on to more recent ones such as MaximSP, which is a graphical patching language, and I'll show an example of that, and SuperCollider, which is kind of a object-oriented, small-talk-based, text-based audio synthesis language. And just to give you an idea, and of course, along with how these tools changed, the way we actually made music with them, of course, changed drastically. So this is an IBM 360, and people did make music on this very type of machine. But of course, back then, the workflow was very different. You had to actually figure out how you wanted your sounds to sound like ahead of time, and then you would make your punch cards, submit them in batch to your local center if you were lucky, and sometimes driving a few hours to the nearest computing center, submitting it as a batch. And the computers back then weren't awfully fast, so it would take hours to days to sometimes compute even a small segment of audio. And so the turnaround time was massive. You know, to hear like a minute of audio, you sometimes had to wait a few weeks for the thing to actually come back to you in digital or some kind of digital analog converted format. But that's the way it was, and that's how kind of the pioneers of computer music actually, that's how they had to work back in the day. And of course, computers got faster. In the 90s, real-time processing of audio became, a real commodity possibility. And we have programs such as MaximSP, which is, here's an example patch in MaximSP, which really came from the analog modular synth paradigm of having modules that we interconnect with patch cords. For example, in this case, the resin tilde that we see here, there's actually 3 instances of these. These are filters, and the yellow striped lines going through represent audio signal flow through here. And then, of course, you can control parameters of these things through these black lines coming from different numbers and also other unit generators. So the idea is that these modules, which we come to call unit generators, are what's really processing and generating the sound. One thing I will point out that's very relevant to this talk is that in here we kind of see at a glance what is going on, and that is great. But one thing we don't so readily see here is when things happen. And that's in a sense kind of what largely this first part of the talk is about. It's about time and how we actually reason about and program that in a programming language. So that brings us to ChucK, and I'll give you some quick ChucK facts. It's text-based, general-purpose programming language, but it's been tailored for real-time audio synthesis and analysis. It's open source, cross-platform, and it's kind of designed from the ground up, so to speak. We just decided, well, let's just start over. But certainly it has been influenced hugely by a lot of the languages that's come before it and some of our own warped, crazy ideas. So, as a roadmap of the first part of this talk, we start with ChucK, which is the language. That enables, among other things, this kind of idea of doing things on the fly. This is kind of the opposite of actually submitting your batch and waiting for weeks for your sound to come back. This is doing things on the spot and using it to experiment with sound in a rapid way, and also maybe to use that as a performance technique. That turns out to be fun, but kind of cumbersome and hard, which then motivated this whole other thing called the article, which is kind of the environment for ChucK, for programming ChucK on the fly, which also visualizes ChucK. So that's kind of the continuum of ChucK and its many disasters in many forms. So let's get on with ChucK. And a word about the design. So this is kind of where our energy went. We really felt that, this is kind of for the first time in history of computing, we have computers that not only can do things in real time, but, well, we felt like it's time to start abusing them a lot more than we have before. And so we don't really care about performance so much. But our question and challenge was, how flexible can we make it as a language? How expressive can we make it as a language for actually generating sound and working with music? So flexibility and readability are kind of our primary goals, and we kind of don't worry about performance just yet. It kind of goes with the make it work, make it right, make it fast, kind of in that order kind of approach to development. And maybe someday we'll make it fast. So on to the core language features. Okay, this is the ChucK operator. And if there's one slide you want to remember from this talk, Remember this one. And it's just equal sign or greater than. And this is kind of an overloaded operator in the ChucK language through which almost all the work is done. And it's context sensitive to what's actually being chucked from left to right. So its operation actually depends on its context. So as a kind of a basic example, if we had some value x of some type, and then we have some other value y, we can then just chuck x to y. That's how we read that particular statement. What it does completely depends on what type of thing x is and what type of thing y is. And then we can also chain them together from this left to right kind of way. So we can say w to x to y to z. We can nest them to specify some kind of precedence. In this case, we chuck w to the result of x chuck to y, chuck that to z. And then there's a whole family of ChucK operators, starting with the unchuck operator, which undoes what the ChucK operator does. And there's a plus ChucK, there's a minus ChucK, times ChucK, mod ChucK, you name it. And more recently, we've come up with a very important upchuck operator. And this is actually the newest addition to the language. And it has to do with actually chaining not just synthesis modules together, but analysis modules called unit analyzers. And I'll talk a little bit more about that as we go on. Not yet, but we are working hard on a potential downchuck. This is kind of name-driven research at its worst.
Everything should be portable, right?
Excuse me? Yeah, we should.
Everything should be portable, so you need a downchuck.
Yes, we do need a downchuck sometime. So that's under development. Oh yeah. So if you have any questions, yeah, just blurt them out, yell them out, and I'll be happy to try to answer.
Can you speak a little louder, please?
A little louder?
Yes.
Okay. So that's kind of the first part of the ChucK language, which is kind of this massively overloaded operator with which we do stuff. We haven't really done anything just yet. So now let's talk about time and actually give you an example of the code. So this is an actual line of working ChucK code. It instantiates an impulse, we call it I, and we chuck it to the DAC. Those of you familiar with audio synthesis parlance might recognize the DAC as kind of the name of the digital analog converter. That's really an abstraction, basically, for your real-time sound card. So by connecting something to the DAC, we're saying, I want to hear what this sounds like. And then we can specify some kind of control structure. Here we say, while true, and in ChucK you actually end up writing a lot of infinite loops. I think my dissertation will contain more infinite loops than most CS dissertations. But that's kind of how you work with ChucK. And in this case, we simply do some action. For example, set the next sample of the impulse by chucking 1.0 to I dot next. And then we do this very critical operation advancing time. So this ends up generating an impulse train of a period of 100 milliseconds. And in fact, a better way is let's go ahead and see this and hear this. There are a couple ways to run ChucK. I'm going to run it in an environment called the Mini Audicle, which is an environment that Spencer Salazar and I have been working on. And this is just a little IDE for ChucK, and that has the ChucK virtual machine kind of integrated into it. So what I'm going to do is let's generate a slightly different signal, and let's see. Can everyone see that? And I'm going to chuck that to the DAC. I can then even say set s.freq to 440. So in these two lines, what I've done is I've instantiated a sine oscillator. I've given it a name called S, and I've connected its output to the input of the DAC. Then I've taken 440 and chucked it to kind of the frequency parameter or property of S, which is a sine wave. So we intend to generate a sine wave at that particular frequency. And I'm going to go ahead and start this and run this file. And actually, it ran successfully, but we don't hear any sound. And that's because we haven't done anything with time yet. And that's the most critical step in ChucK when we talk about time. So at the onset, we can just do something very simple. We can specify duration, say 1:::, second. You can just read that as just 1 times 1 second. And that's a duration then we chuck to now, which is this other special and very important reserved variable in ChucK. It actually represents the current ChucK time. And the more formal way to write this might be to actually plus ChucK 1 second. Basically, we're incrementing the ChucK time by 1 second. And this is what allows sound to actually flow through the system and be generated. So let me turn this down because it's not entirely pleasant. There it is, for 1 second. And of course, you can continue this and say, aha, now I can generate a melody, perhaps. And I'm just going to double the frequency and then take a quarter of the frequency. So, in fact, I'm going to say 0.5, 0.51. And that would sound like. All right. So, but that's kind of a straight line program. We can generate things. It's kind of a tedious way to do that. So let's put a little control structure around that. So here we put our infinite time loop around this, and that'll just keep going. Well, that's even too tedious for me. So I'm going to do is generate a random number between 30 and 1,000, and then chuck that to the frequency every 0.2 seconds. And that's a little slow, so I'm going to do that. Okay, so now we've arrived at kind of the canonical sound of what computers are supposed to sound like. But why stop there? So this is equivalent to 100 milliseconds. It's represented as that. And by the way, what I'm going to do here is actually going to say replace the shred, which means rip out the current running process and run this one instead. So it shouldn't be any difference there, really, because I'm just doing 100 milliseconds. Let's do 10. 1. If we want to be really crazy, we can actually randomly choose a frequency in ChucK every digital sample. This is really, as far as audio is concerned, the lowest granularity we can actually change things at. So let's do that. I added instead of replaced. That's what that by itself sounds like. And that's actually what you should expect. We actually are hearing, that resonance we're hearing is actually the average of the range. Since it's a uniform distribution, it's actually a little bit above 500 hertz. That's actually what we're hearing. And this is actually statistically what we should be hearing. And this is something that's pretty unique to ChucK. It's kind of this ability to mold time in a completely flexible and deterministic way. There's really no limit as to kind of how small of granularity, other than kind of floating point precision, as to kind of what the time scale you have for manipulating things. So this actually doesn't make a lot of sense, but we're actually changing the frequency 10 times per audio sample. So since my audio sampling rate is 44.1 right now, that's actually changing things 400,000 times a second, which is kind of meaningless, but you can still do it. I'm not going to for now. But let's go the other direction. Let's say we have seen millisecond, we've seen second, we can do a minute. I'm not going to do this because it would take a long time. There's hour, day, and week. And these are all kind of basic durations you can work with in ChucK. And we kind of stop with week because month is kind of hard. Because there are different number of days in a month, and you have leap years and such like that. But if you, the programmer, you can actually define your own notion of a month or really any other musical duration that you want to work with. Someone did suggest fortnight, but we're kind of still in debate as to whether to add that to language or not. So that's kind of ChucK time in a nutshell. So let's go back here. Hold on a minute. Let me just stop this. I'm having some weirdness with the PowerPoint. I think ChucK is pretty good at interfering with the rest of your computer. So I'm going to restart my PowerPoint. Hopefully that will work better. Basically, when working with ChucK, the command kill all ChucK comes up very much on the command line. So let's see, where are we? Let's go with this. All right. Wow. So as a summary, duration, or dir, is a native type in the ChucK language. And the default units are milliseconds, seconds, all the way to week. And then you can perform arithmetic on duration. You can say 1 second plus 100 milliseconds is my notion of a quarter. And then you can turn around and say 4 : quarter is my notion of a whole. So you can kind of build up a musical duration vocabulary that is most appropriate for what you're working with, using these as kind of starting points. And then similarly, time is a native type in ChucK. So duration, which is the length of time, and time, which is just the point in time. And the now keyword is of type time, and it holds the current ChucK time. And you can also perform arithmetic on that. Say 5 seconds plus now. You can say that's stored in a time variable called later. And you can say things like, while now is less than later, do stuff. And an important thing to realize about time is that time stands still in ChucK until you choose to advance it as the programmer. And through 2 semantics of doing that, you can chuck a duration to now, which we've seen, which essentially increments it, but it also kind of makes the current process essentially do a very fine granularity sleep there. By fine granularity, I mean sample synchronous. It actually waits on that particular sample. Or you can wait on a particular asynchronous event for that to be triggered, meanwhile letting time advance. So those are the 2 basic semantics of advancing time, and you, the programmer, are responsible for keeping up with moving through time. So that essentially makes kind of this equality between time and sound, and furthermore between kind of time, sound, and the code that we write. So embedded within the code, we actually see timing. And so that's the ChucK operator and then timing. And then let's go one step further. Let's do this not only with one kind of flow of logic, let's do this in parallel processes and to synchronize them finally. So we have concurrent audio programming, which the idea here is that we still have kind of some kind of a signal flow up here. It's an impulse, just a click generator that goes through a filter. It's a biquad filter that goes to the DAC. It just filters the impulse. And then maybe we want to generate the impulse at a particular rate. In this case, we generate an impulse every 80 samples. So it's an impulse train with a period of 80 samples. And then we also want to sweep the center frequency of the biquad. Basically just changing parameters in the biquad. We want to do this at the same time and potentially at a different rate. This, for example, is changing at 50 milliseconds. And let's see what that sounds like. And I'm going to show you a quick example here. So we're actually going to we have this program called mo.ck, and this is just going to sound like this. Whoops. That's essentially our impulse through the biquad. This is only one kind of process in ChucK, but Mo has friends. So we have Mo, and then we have Larry, and Curly. Curly's a little weird. Okay, but they're all essentially generating impulses, but at a similar but not exactly the same rate. One is going at 100 milliseconds, one is going at 101, the other is going at 99. So if I want to run them all together, I'm going to say Mo, Larry, and Curly. And just to zoom in on this, that's the command I'm actually invoking. You kind of hear this kind of phasing in and out with each other. And that's the idea behind concurrency. This is a very kind of not a very fine granularity example, but it's an example of just having a program kind of worry about its own timing and then kind of throw it into the mix with other programs and just having it work. And ChucK concurrency is implemented using what we call shreds, which resemble non-preemptive threads. And in ChucK parlance, when you want to spawn a shred, you spork it. It's kind of like forking a process, but you spork a shred. And the really key thing to understand about concurrency in ChucK is that different shreds of execution can actually be synchronized automatically by time or events. And so, like I said, if you have different parts of the program that worry about their own timing, you throw them together, they will work in a sample synchronous kind of way. And this can work at a high and low level, and it unifies this notion of control and audio rate. So if we think back to the Maximus picture, we had yellow lines connecting modules and we had black lines. The yellow lines are for audio, and then the black lines are kind of for control. And it's always been this historic debate in the computer music community as to what is the right control rate. And control rates, again, is a bit of background, is there because it's kind of, a lot of control doesn't need to be asserted every sample. It just needs to be asserted at a perceptually acceptable level. But a lot of different synthesis processes require much finer control rate than you might provide. So the debate's always been, what is the right control rate? Well, ChucK would just say, you define your own control rate. In fact, you can define your own control rate just as a product of how you actually code up your programs and how you advance time. And you can have many of these potentially going at different control rates. And this all gives rise to this notion of what we call strongly timed. And what that means is that programs have precise control over their own timing with sample synchronous control that can be asserted at any unit generator at any time. There's no fixed control rate, and there's this clear separation of data and time. And this transfers the primary control over time from kind of implicit scheduling engine in the language or environment to the language itself. So the programmer can actually have access and control over that. Program flow is equal to time flow, and this kind of encourages staying in the language more. So in a lot of these environments, such as Maximus V, SuperCollider, if you want something that requires a much more finer granularity timing, for example, granular synthesis, or some process that operates at a very low time level, you end up coding these things in an external language like C or C++, compiling it with their API, and then basically importing it into the environment as an external object. In ChucK, what we hope to do is to kind of encourage more of a sense of experimenting directly in ChucK without having to go to these other languages. So you can just represent and express more from the language out of the box. And this provides kind of a natural modularity, this idea of time and concurrency for on-the-fly programming, which we'll get back to. But first, a quick bit on implementation. So the ChucK is a virtual machine language, and here's how things work in runtime. So I have some code, say foo.ck. We send that to the on-the-fly compiler. That gets compiled into a process consisting of one or more shreds, which are in turn scheduled by the ChucK scheduler and executed in the ChucK execution unit, along with an audio engine and I/O manager that comprises the overall ChucK virtual machine runtime. And of course, you can just keep chucking code into the on-the-fly compiler. Another view of the system is the following. So I have a type system that types check and emits the code, and then the runtime compiler will send these new shreds containing virtual machine instructions to the VM and scheduler, which then queues the shreds, sorts them, and gets them ready to be executed. That's going, and then as each shred executes, it's executed in this bytecode interpreter. And there's an audio engine kind of managing this global unit generator graph. Remember, these are the things through which audio is actually computed. And each active shred has the option of actually making modifications to the graph or asserting control at any one of these nodes in the graph. There's an I/O manager for actually listening to devices such as mice, joystick, Wii modes. And you have a listener that talks to other ChucK processes from which you can gather statistics and display them. And the bytecode interpreter operates on one shred at a time, has a memory stack and operand stack, pretty standard, and each instruction has a well-defined behavior with respect to the stacks. And then we have about 100 bytecode instructions that range from add flow to more specific ones like advanced time. And so that's kind of how the modules are related. And the scheduling algorithm is quite simple. This is for a single shred case. So we start and we suspend the shred, basically runs suspended, and we say, is it time to wake up the shred? And we infer that from how it advances time. And then if the answer is yes, then we resume it and run it, and then until the shred actually advances time. So in a sense, a shred is kind of like a non-preemptive code routine of sorts in this case. And if the shred doesn't need to be wake up at the current time, we then traverse the unit generator graph, generate the next sample of audio, and then we advance time, or now, by one sample. And then we go back and say, is it time to wake up another shred? This is actually really simple and pretty easy to implement, but of course it's kind of slow, and we'll get to that.
So shreds start, state of time to wake up?
Shred actually, that kind of depends on how the code goes actually. Shreds actually, when they start executing. So this is not entirely accurate, but they kind of start in the scheduler, and then the scheduler just starts running the first one that needs to be run. And then this is the more general case. This is the multi-shredded scheduling algorithm. So we say, currently, are there any shreds left at this current time? This is kind of more of a steady state picture. And we say, if there's no, then we're done. If there's more shred waiting to run at this current time, we say, run the next shred, and then the shred does its work until it advances time. And if not, we traverse UGen graph, compute next sample, advance time, process any incoming messages, and then we go back to the center question again, more shreds waiting to run now. So basically, all the shreds are sorted by the time at which they need to wake up next. And then we run them in order for at a particular time until there's no more shred waiting to run at that particular time. Then we generate one sample of audio and then see if there's any more shreds that need to run at the next sample. And that's kind of, in a nutshell, how the system works. And audio computation are controlled by the shreds because the shreds, remember, set the parameters to these unit generators. But they're actually computed in the virtual machine outside of the shred computations themselves, usually. Because we have these kind of unit generators, which are usually written either in C or ChucK, that actually process the audio. And you can, in addition to doing synthesis, you can also do analysis via what we call unit analyzers. And these are actually manually triggered from user code. Whereas the audio samples are kind of saying, anytime you need a new sample, you go kind of work backwards from your DAC and say, you kind of do a pull through the graph and say, give me the next sample. So just to give you a quick example of analysis, we go back to the upChuck operator. And this is kind of just for your reference. So we have ChucK, and then we have upChuck. Note how the direction of the arrow is pointed up. This is we usually use this to work with kind of data in the transform domain, such as in the Fourier frequency domain. In this case, it's kind of an orthogonal dimension or something. This is why the upChuck is pointed up. So there's no other good reason. That's not even a good reason, but there are no other good reasons for that. So here's a quick FFT example. So we have some audio input, and then basically what we can do is use the upChuck operator to connect unit analyzers together. For example, we can have our input, which is an audio input, chuck that to the FFT object we call FFT1. Then we can upchuck that to the centroid, which is extracting the centroid, which is a spectral feature that you can get from a frame of audio. And here we're just trying to get some characteristics of the sound at a particular time. And then we have the FFT1 go into a flux, another feature extractor, and then the input on the third line going into another FFT object. And then you can spork off different pieces of code here, which go through time and perform kind of this multi-rate FFT analysis and feature extraction. And the idea is that you can read this code, at least have a chance of reading this code and inferring exactly when the FFTs are taken, when these feature extraction is taken. So this is kind of a quick example of like kind of multi-rate analysis and synthesis. So that brings us to the next thing in ChucK is on-the-fly programming. And remember, we have a ChucK operator, we have the time, and we have concurrency. So timing can be used to basically synchronize everything together that's actually running concurrently. And we use this to our advantage, or try to, in on-the-fly programming, in which we define as the act of modifying the logic and structure of a program during runtime for the purpose of rapid experimentation and exerting expressive control, also called live coding. And a historic note, this is the League of Automatic Composers who are actually working on live electronics, tweaking them on stage for performance. I don't know, that always looks like a toaster to me, but if it is, it could be. And they're doing just something really insanely creative with it. And 30 years later, we have on-the-fly programmers, and not much has changed. Less electronics, all is in the computers. We have a lot more mice on the table. We're still using tables. And that's kind of our vision for doing on-the-fly programming. So I'll give you a quick demo. What's that?
You need a wireless mouse.
Yes, I do. Yes. That's a very good point. So what I'm going to do is give you kind of an example of very rough on-the-fly programming. And there are many ways to finally kind of craft things on the fly. This is not one of them. This is just, again, taking a piece of code, pulling it out, shoving a new piece of code into it, but you can synchronize them together pretty well. So what we have here is this code that starts out not making any sound. Let's see what's going on. It's kind of on-the-fly debugging right now. This is really low for the speakers. So here what I'm going to do is just start changing stuff. So we just have like one note in our pitch array of pitch classes. I'm going to say let's add a second to that, and I'm going to replace that. And here, by the way, I've randomized kind of a register, so it's shifting into different registers. Well, why stop there? Let's go and add a major third, replace that, a fifth. It's make it a little faster. add a sixth. Change the register a little bit. I'm gonna add a seventh. And then, well, let's make it sound a little bit nicer, add a little reverb. And a little faster. And faster than that. And the idea is they can just kind of keep going and just work with your composition in a very live and on-the-spot kind of way. So that you don't have to really pause, recompile, go back and say, is that the sound I really want? You can just kind of experiment with it right there. And that's kind of what we're after. And there are actually ways to actually build systems for which you can actually hear the transitions on some of these when I actually replace a piece of shred. There's a slight click in the audio and there's interruptions. And there are actually ways to actually get around all that if you build more sophisticated systems. But this is kind of an example of how, to actually start manipulating sounds and just experimenting with stuff. And everything is kind of using kind of this framework. So let me go ahead. Yes. Oh, right. MTOF stands for MIDI to frequency. So what I'm doing is generating pitches. That's essentially MIDI pitches, where 60 is middle C. And then this actually converts it to frequency in hertz. All right, any other questions? Yes?
When you switch to another an updated version, do you retain some state or do you start from scratch?
In this case, you don't retain state. There are ways you could, for sure, yeah, if you want. You can actually code up kind of a repository or kind of a shared object that actually keeps state. And then the code itself will not have state, but you can definitely specify for state to be shared and
Otherwise you
updated.
get too many glitches, basically.
Right. And there's definitely better ways than what I've shown you to actually do this in practice. So let's quit that and hopefully PowerPoint will behave. Okay, the power tools can MAME. So we performed using this thing sometimes. And you have the power to spork many shreds of sound. And you can precisely synchronize each shred if you want. You can edit and resport, you can query for status, but oops, which shred is which? Which shred is making what sound? Which version of the edited code did I save? Who's using all the processor cycles? What's the relative timing of the shreds? Who's clipping? All of this leading to a state of confusion for which we have the article. At least that's kind of the initial thinking. And the idea behind the article, as I'll show you, is that we have kind of the traditional kind of programming pipeline. If you do some editing, you compile it, runs on some runtime platform. There's a problem or you don't like the way it's behaving, you go back and you debug it. So that there's this kind of divide between development time and runtime. What we hope to do is kind of narrow that a bit so that you can kind of just keep working, as you've seen in my little demo there, so that runtime and development time can be more of the same thing. So the article is really about kind of trying to do things on the fly, but also it's about visualization, about visualizing audio, runtime stats, scheduling, and it's about kind of at a higher level insight into the real-time live programs that we're writing. And it does so by providing different views of the programs. We can look at code, we can look at shreds, we can look at timing. And it's also a different view of the programming process. And quick one design is tightly coupled with ChucK, and the editor, compiler, VM, debugger all run to the same address space. It's a giant flaming disaster. As a command line, but also a graphical interface, and it synchronizes graphics and sound in the same framework. It's extensible, which means it's not done. And it's interfaced via the AutoCube. And so another view of the design is we have ChucK and the article. They don't talk to each other directly, but go through a mediator. And those we just send statistics, hooks, values over to be visualized. There's a graphics engine, a UI engine, a console for typing stuff into, then a manager of faces, which manages the different aspects of the article, which look kind of like that. So we kind of have everything mapped onto the cube in a kind of a hacked, fast user switching type of way. I'm not sure why that's actually useful. It just seemed like a good idea at the time, but so far has not been at all advantageous. At any rate, so we have different things for representing different parts of the system. Editing, compiling, sound, time, etc. So let me give you the AutoCode demo right now. Okay. So we start in the Shreditor, and that's the editor of ChucK, of the article. And what I'm going to do is I'm going to load up a piece of sound like that, and throw it back into full screen. It's a little low. So what we're going to do is we're going to start editing in this. And this is kind of like the mini article. Say, boost that by a couple of octaves. So notice when it did that, new revision kind of appeared here. Say, this is a different version of the code than that. What I can do is actually drag this into this new version to actually switch it. That's kind of the replace operation. And then we can keep working with this if we want. So, for example, if I can add the reverb back, and then drag it, and maybe just a little higher. So you can go back and spork off more shreds if you want. And by the way, these are actually programmed to actually be in sync with each other, so it doesn't matter when I add them. They kind of find out about the timing and they start twinkling at the right rate. And so that's kind of the editor phase, and this is meant as kind of a out-of-the-box performance interface. So you can go on and take this on the road and project it to the audience. And half of live coding is really about showing the audience how you're doing this thing. So when we perform, we project our code, our screens, so we're not just checking email or like playing on iTunes. And we're actually doing some non-trivial work. It doesn't always work, but at least we try. And you can make mini buffers, and this is one of the only buffer systems I know of that actually has a really bad physics engine built into it that allows you to kind of throw things around until you find a piece of code that you're looking for. You can also zoom in the code if I remember the command. And this is kind of like basically saying, look at my beautiful piece of code right here. Just basically to gain attention to a piece of code. And you can also look at things all at once. So that's kind of the Shreditor. Let's move on to the next phase. And that's to show you kind of the audio that we're generating. Can you guys see this okay? Do we need to dim the lights? Okay, thank you. So the top is actually the audio waveform. The bottom is a short-time Fourier spectrum of the sound. And we can see the sound in a spectrum scrolling past us. And through the miracles of OpenGL, we can abuse this in very easy ways and basically look at it at different angles. We can also check out, transform it in different ways, applying different transform windows and seeing how close we are to clipping and things like that. So that's the VM space, and this is just for visual feedback on the sound you're generating. It actually turns out to be a really useful tool when you're actually generating sound. It doesn't sound quite like what you want. You just look in this thing and see, oh, that extra frequency shouldn't be there. Like actually when I turn it on here, that was actually reading from the microphone. I was seeing a resonance that I was hearing. It actually turned out to be coming from this monitor. Anyway, so the next part of this is what we call the shredder. And the shredder is about shreds. And here, this is a really meaningless view of 3 shreds that I started here, 1, 2, and 3. And they just keep twirling. The size, the rotational speed, and the color doesn't actually mean anything yet. We still got to map this. This is still just really bad idea so far. But we can also look at it in kind of a top view, which is just saying, kind of what it's doing. Because shreds compute at a particular time and they basically wait and go to sleep until the next time, we're always catching them in a waiting state. But if a shred misbehaves and actually does not advance time in a timely manner, then you would actually see it as running here. You can actually physically go in and kill that shred. So it's kind of our manual hack for compensation for our halting problem. So that tells us what's happening with the shreds. And by the way, this is the number of virtual machine instructions that's elapsed on that shred. And then this is kind of an average control rate. That's how often the shred is advancing time. And here we actually see the relative timing visualized. So what I'm going to do is I'm going to remove these guys and show you, no, not that guy. How about OTF 07? And you can see kind of how every time there's a spike, it actually means that the shred is waking up to do some work. And those correspond right now because they're actually triggering the drum sound in this case. And we can see more things are happening here. You can see that this running average is actually trickling down whenever you hear kind of this flurry of notes. And let's go ahead and take that out. And let's add yet another group of guys. these are program shreds that again know how to synchronize with each other. So let's add that. A little bit of a snare. And the idea here is that you can kind of get a program from someone that makes sound, and you can run it in the article. And before it, you don't have to know what the code looks like. You can kind of see how it behaves, how it sounds, what type of sounds it's generating, and how the timing actually work with each other. So let me add a couple more things. So these are more shreds that actually themselves create and spork more shreds. And these shreds basically just make a whooshing sound and then they leave. And so this is a slightly more different scenario for this. What we can do with this view is also kind of position things differently. So we can say now is on the very left, and we can kind of zoom in and zoom out on the history of kind of the program I'm running. If we go back here, things get a little crazier. Basically the way this works now is that when a shred is still actually working on stuff, it's in this plane of existence. When a shred is done, it leaves and goes to shred heaven up here. So it's another really bad visualization of things here. And then this view also gets kind of crazy because you can just also get a history of what's actually happening just a little while ago. And then the future of this thing is we're really trying to bring this into kind of a social collaborative kind of a space, so that I don't have to be the only one sitting here. We can each have a laptop, and maybe in one place, maybe all across the globe, and log on to the server and writing music together and via code. And we can jam together, hear what each other's doing. There'll be a notion of kind of a leader where you have a halo, I guess, and then you can actually carry around a bindle that has your sound, your code, and things you can share with everyone else. So that's kind of in the works at the moment. And you can also, of course, dance together if you want. Of course, he jumps through the halo. So, and let's see, what else can we do? All right. And, all right, so that's the article in a nutshell. Uh-oh. I've gone back a little bit. No. Excuse me, I'm going to fast forward my slides. Okay, so here's some feedback about ChucK. This is a random sampling of positive feedback we've gotten from ChucK. Just enter the world of ChucK. I'm happy. I'll just let you read this. There's a really geeky one. A computer, ChucK to music. There's no better dot mix, etc. Okay, so that's people happy with ChucK. Here's people less happy with ChucK, etc. So we're still working out all the things. It's not the fastest thing you'll run under the sun. In fact, it's probably slower. You can run less things than pretty much all the other environments for making sound. But we're hoping with ChucK you can do things within the language that you can't with any other language. And we're just hoping to kind of provide a different way of thinking about time and concurrency. And that's our goal. And if we can do that, we're happy. And so in summary, the design solution for ChucK was to make time itself computable. So the time and duration are native types, allow a program to be self-aware in time, and allow the code to schedule itself. And you can synchronize concurrency via time or events. And our goal is always, because computers are so fast, we can abuse them, we're going to just try our best to keep hiding the mundane and just try to forget as much as possible that we need to actually make this run on a machine, but really think about how to make it the easiest thing to use for a human, and to expose true control, and to do everything as much as possible on the fly. So that's ChucK, and this is where you can get ChucK. It's open source, and it'll crash all the different platforms with equal grace. So any questions before I move on to laptop orchestras? Yes?
Talk about documentation and pedagogy side of this language.
Yes, actually, I will talk more about it when we get to the laptop orchestra, but to give you a quick idea right now, ChucK is actually being used now in quite a few universities around the country and even around the world. It's being used at Princeton. We've been using it for the last 3 years to teach in laptop orchestras, audio synthesis classes, music, computer music in general. it's kind of the primary tool for actually teaching in the laptop orchestra and also for making pieces. We're using it here at Stanford, and it's being used in places like University of Victoria, Georgia Tech, Barcelona, Virginia. The list goes on. It's just being used as another tool for generating sound. And our goal is to really make this thing as easy as possible for people to start running with it, but also making it really flexible and powerful in this kind of sound and music you can generate. So I'll give you more of an idea when we actually go down to the laptop teaching section. That's a great question. Any other questions? I'll have more questions. We'll answer more questions at the end, but if you have any burning questions about ChucK. Okay, so shall we move on? Laptop orchestras. So I'm just going to start with PLORC, which is the Princeton Laptop Orchestra. And it was founded by 2 professors and 2 grad students in 2005. Dan Truman Perry, my advisor, are kind of the professors, and Scott Smallwood, he's a composer and grad student in computer and in music at Princeton, and then myself. It's 2005, and it's a group of 15 meta instruments, which is a laptop, a speaker, human, sensors, making music together. For making what we like to call electronic chamber music. I'll explain more about that. And so the 4 of us put everything together in 2005, and we've been developing it for the last 2 years. And what I hope to do today is to introduce this to you, but also to lay out, formally lay out an announcement for starting the Stanford Laptop Orchestra, which we actually have a go-ahead to do, and which hopefully will happen by this spring. So for that, as you will see, we'll need a lot of programmers, players, designers, and people to evaluate the thing. But I'll get to that. And my goal in this was, well, first of all, I should start with kind of the idea for the laptop orchestra. This is a picture of PLORC in performance. And as you can see, the 15 laptops, and this is actually in performance at Princeton with the renowned tabla player Zakir Hussain, who is actually right there, playing with so percussion, that's who's actually processing his sounds. And then the players have a score in front of them, they're processing their own voice, and we have these crazy E-tubes, PVC pipes with contact mics that we're slamming down on the ground. This is just one piece in PLORC. This came out of Dan Truman's thesis. He had an idea in his thesis about making this electronic chamber music with a group of musicians. And the idea is that, you see, there's no other amplification to what you see here. Everything is in this picture. And if you get a closer look, a PLORC station consists of a laptop and rack, which has an audio interface, power conditioner, amplifiers, that drive the 6-channel hemispherical speaker. And the idea behind that is that instead of using the traditional PA system, as we have here and also in many concert halls, we want the sound to be intimate and come from right next to the instrument, i.e. the laptop and human. And we have 15 of these, totaling a 90 different independently addressable audio system with 4 subwoofers. And the idea is to give you a totally intimate feeling of sound that just kind of swallows you and inundates you. And it truly is a very different experience than the PA system. It's kind of its own beast in a very cool way. And so Dan and Perry got funding for this back in 2004, 2005. And then in 2005, the 4 of us started to build this. My role, in addition to kind of providing ChucK and supporting ChucK as the kind of primary platform I could post for it, I also ended up being kind of the principal conductor of the laptop orchestra. And also I'm there just to make sure things don't catch on fire, which they can. So the challenges of the laptop orchestra are many. This question is really, how do we make instruments for the laptop? I have the laptop here, but this, as this sits on my desk right now, is not an instrument. It's just a laptop. It's a blank slate. And the question is, how do we make instruments that engage the performer out of laptops? How do we make instruments that engage the audience as the players perform them? What types of sounds can we make? How to compose for it? How to organize a dozen or more players in this context? How to conduct it? And so these are the things we had no idea what the answers to when we first started this, but hopefully we gained more of an idea as we went on. This is a picture of things in performance. Actually, the best way for me to do this is actually show you some videos, which are right here. So let's start with this. So this is Plork in rehearsal with Zakir. Wow. And we used a variety of sensors. For example, we see accelerometers, tilt sensors. We're actually connecting to the laptop, controlling the drone. With players, actually, there's Zakir in the front, and with players in the first front rows actually receiving his sound and processing them. There's Dan. More accelerometers. I'm going to just move forward in the interest of time. Moving on to the next piece, which is called On the Floor by Scott Smallwood. So this is a piece for laptop orchestra that tries to simulate the soundscape of a casino. If you walk in a casino, you notice all the machines are actually tuned to the key of C major, and so in this piece, the players are actually gambling on a virtual interface. And this is the monkey cam walking through the stage. That would be me holding the camera and crawling through the stage. And this piece will continue to build up, and players are encouraged to show their emotion as they win or lose. But as time goes on, people will start losing all their money. And by the way, Scott, he's the conductor. He's the house. So he actually has a patch that he can monitor and surveil the players. So if they're winning too much, he can actually drop their odds, so they start losing. It's very important that this piece doesn't go on for like 20 minutes. And all right, so next piece is a piece that Perry and I, this is actually our first piece for the laptop orchestra. And in this piece, we try to be a gamelan ensemble. We have a networked step sequencer interface running on a machine that's synchronized across all the machines through ChucK. And that's what the interface looks like. Perry actually has a printer sitting next to him in front of the stage, actually printing out the instructions in real time. And it's all very on the fly. He holds them up to the players, which specify what sounds to play and how dense to make it. And players construct patterns in the sequence. And then when you kind of sum them all together in a very well-synced way, they actually sound good. It's actually very hard to sound bad in this piece. And then we'll slowly move to like a drum sound. Any way you can get more bass on the sound system? Thank you. This is a piece by Dan, and it's all about kind of making drones that have very interesting, rich spectral characteristics, and then varying them in slight ways to make them kind of interact with each other in cool sonic ways. And here we use a variety of tilt sensors, Wacom tablets. We have trigger fingers, which are essentially touch-sensitive pads, and then just the computer. In this case, Dan, who's actually sitting off stage and sending instructions via text to the players. There he is. Okay. So that's an idea of kind of what Plork sounds like. Those are actually all from the first semester. Since then, we've written, now there are probably 50 pieces now or more that have been premiered for the laptop orchestra. Most of them are actually in ChucK, but we also work in Maximus P, SuperCollider, with pieces written in Java. And we don't really shy away from anything, so we add different sensors to it. These are just examples of not sensors we necessarily have hooked to Plork, but just sensors that people might hook to Plork. Biofeedback systems. This is actually Dan's Bossa, which is kind of the grandfather of the Plork hemisphere speakers. He plays kind of a violin bowed interface, and that goes to this this ball, this bossa, this speaker array that's actually sitting in his lap sometimes, and the sounds is coming from him. It's great. And then he played a duo with Curtis Bond, who's a bass player at Rensselaer Polytechnic Institute, and he plays censored bass with these crazy spherical speakers. There's Perry operating a controller he's making called the COW. That's spelled COWE. Stands for controller, comma, one with everything. That controller he has linear force sensing resistors, buttons, has tilt sensors, has a breath sensor that you can both like blow into and suck air out of. And he's actually controlling the air with a stuffed cow that he has under his arm. So it's kind of like a bagpipe. He squeezes the thing and it blows into the interface and makes sound. That's a beat bug from MIT/Georgia Tech. People playing it. So these are all things we could connect to Plork to make sound. We also make software interfaces, such as the one we used in the Gamelan Orchestra. So this is what the interface looks like to the player. And this now cursor is actually the same, it's synchronized across the orchestra. So everyone sees this picture, and they choose colors which represent their sound palette, and they drop them down on here to make different sound patterns. And people are encouraged heavily to listen to their neighbors to actually figure out what to actually play next in this and many other pieces. This is the gambling interface. I won't show you that live for the interest of time, but basically you just click on one of these spheres and crazy colors appear and you win or lose money, and that's it. This is one of the more crazier interfaces that Scott and I did. This is called ChucK Rocket, named after the Sega Choo-Choo Rocket game, and if I'm lucky I can maybe get this running. Hello, there he is. Okay, so in this case, we have a game board with 1 or 0 or many mice running on it. And what we can do is put arrows in their path and they'll follow it. But more than that, we can put sound objects in their path, and when they run over that, they'll make a sound. I'll put another one here. They kind of eat each other up when they... And the idea is that this is also kind of a shared experiment. Let me turn this down. Let me remove that. And what we can do is actually, all the mice in the ensemble is actually shared between the players. So you see these two things here, they're actually portals to your neighbor's machine. When we run this, it's a giant ring of machines, and we can actually send mice from one machine to another. So we share kind of all of these like running critters that are going through the world. And also, furthermore, timing is synced. Even though they're running smoothly, it's actually a grid-based system. So if I construct one pattern on my machine and you construct another, chances are they will sync up. And actually, we actually have a fighting chance of creating kind of rhythmic patterns among the entire orchestra using the system. And again, we get to abuse things a lot because it's OpenGL. So let me make a lot of mice here. And things can get pretty crazy, and people will construct mazes out of this. For example, let's see. Let's place something in their path. And it's more interesting when you actually have 15 of these things like running crazy. And so there's that, and a different view of ChucK Rocket. So that's another class of interfaces that we've been designing and building and abusing in Plork. And the final class is actually one that's just based on the laptop itself. So I have a picture of a laptop here, and it has buttons, which is good. It has a 2D position sensor, i.e. mouse/trackpad. It has a microphone. Many of them have cameras. The one I have, and many of your MacBooks, will have motion and tilt sensors. And there's often a ambient light sensor in many of these to kind of figure out how bright to make your backlit display, depending on your environment. And it's got wireless So you can, out of the box, the laptop is already kind of a platform for designing physical-based interfaces for music. And indeed, we tried doing this. So this is one piece we did called Clicks, which we premiered in the Round, which is in this library at Princeton. The audience is actually sitting on the ground floor. We're on the balcony. And it looks and sounds something like the following. This is what I call conducting by arm flailing. So the conductor here basically is choosing the frequencies that they're playing, and the players are actually just typing on their keyboards. So this is low frequency, and then this is high, and the ASCII values of the keys are actually mapped to the pitches. And then a synchronization program is actually synchronizing all of the clicks together. So you just got to type, and things again will be kind of synchronized. So this is kind of our way of, in this piece, of trying to leverage what the computer is good at, synchronization, and being really precise to what the humans can decide to do musically. This perhaps is better, or probably worse, conveyed in a Fox News story about Plork.
You know, years ago, if you mentioned electronic music, people thought of weird machines with twisted wires and antennas.
Kind of like ding, 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 ding. Today we live in a world filled with synthesized sound, and now a new musical group has taken the whole idea one step, or should we say one lap, further. Here's Fox 29's Gerald Copan.
Unlike the usual ensemble, this one doesn't tune up. They set their speakers in place, plug up their cables, and make sure they're sufficiently wired. Then conductor Ge Wang leads them off, and they launch into music that sounds like a combination of bubblegum pops and signals from Sputnik, all in a day's work for the Princeton Laptop Orchestra.
Historically, musical instruments have been at the edge of technological development. Back when Bach and Beethoven were working with their pieces, a lot of the instruments they worked with were cutting-edge instruments. So the idea here is to see what kinds of things we can discover musically with the laptop.
As an extracurricular, about 15 Princeton students take part in the program, each one armed with an apple and the will to make music history, one way or another. Not everyone in the Princeton Laptop Orchestra is a computer geek. Some are engineering students, others are in the music department. And in fact, we asked one young piano major if he thought this sort of thing would eventually put him out of business.
And so I think that this is just a new genre and a new territory of music that can coexist peacefully with piano playing and all the stuff that we've been used to.
Whatever you think of the band, it was proven long ago that electronic music is here to stay. All you need to do is listen to the radio to hear that. Personally, I give it a 90. It's got a good beat. And if you have the energy, you could dance to it. In Princeton, New Jersey, Gerald Copan, Fox 29 News.
Right. Okay, let's see. Oh yes. So our results, we've been trying to build more interfaces based on kind of just the things in the laptop. And Rebecca Febrink at Princeton, grad student at Princeton, and I were a good friend and close collaborator. We worked together on the Small Musically Expressive Laptop Toolkit, or SMELT. And the idea is that we really transform the laptop into a platform for making new interfaces from Laptop Orchestra and for just kind of this on-the-spot music making. Actually, no, let's not see that again. So another one, the next interface I can show you is kind of this thing called the Chrysalis, for another piece that I've composed for the Laptop Orchestra. And this one kind of uses the keyboard mapping here to specify pitch. For example, C, D, E, F, and G, A. And the top is kind of controlling the resonances of filters. And then use the trackpad to actually bow in different patterns, to actually inject energy into different systems, which corresponds to channels of sound. So let me give you a quick demo of that. And for that, if I could have the overhead. Hold on a minute. That's interesting. Got it. I have an external mouse plugged in, and that really confused it. So in this case, what I'm doing is I'm holding it on pitch here, and then I'm just bowing here. Oh, sorry. Can we switch back to the overhead? You can change. So the gesture of the bowing really corresponds to the sound. Thanks. Let's see. So that's kind of this wind-based instrument. It actually sounds very different, obviously, when you have 90 channels of sound going through this, and just kind of this maelstrom of wind that's actually going through. Another similar interface, what we've done is we just kind of went with this, and let's see which one to show next. Oh, so I mentioned that there's actually this sudden motion sensor on some of these laptops. So what we can do here is actually, let's go ahead and run one of those things. It works. No! Okay, so right now this is a simple program that is rigged to detect hits on the laptop. So if I go, no! It just plays a sound. Of course, that could be mapped to much more musically interesting results than this. Or you can do, let's see, motion, drone.
What sensor did you use?
Huh?
What sensor did you use?
That was the sudden motion sensors on these MacBooks. And there's a way to kind of access them. The people who post on the internet, we built it into ChucK, so you can actually just access them. You can actually now connect a Wiimote to ChucK if you want and use that to build instruments. Let's see, I'm hoping this will work. Can I have more volume, please? So in this case, I'm just kind of chanting. But the different vowels are actually mapped to how I'm tilting the laptop. So I have 4 vowels mapped to different corners. Thank you. And then, let's see. And combining kind of this like pitch control using the laptop and also kind of this formant vowel space. Let's run another program. This is a program called Joy. This is a piece called Joy of Chant that Rebecca Perry and I wrote together, and it's a interface for singing synthesis. So, okay, and that uses a joystick. So we still have the same formant model, but instead of mapping it to the tilt, we actually map it to the location of the joystick. So when I click this, it's going to start singing. When I move it, one vowel. All right. When I twist it, vibrato. And then you can just combine it with your left hand to actually specify the pitches. Sound like that. And you can also make it breathe. So, and also a piece we did where we have like 15 joysticks and we're all just chanting and making breathing sounds together. All right. So, let's switch back to PowerPoint if I can. So I'm not going to play any examples of this, but this is a duo that Rebecca and I do, which involves actually a live acoustic instrument, the flute, and we process that. And then we also do kind of droning, beat-oriented thing in a duo that we, in a piece that we call Plork Beat Science. And there's another close-up pictures of that. So 5 stations, they're all synchronized via the network. You can see the airport right there. Just playing the flute, but also controlling these touch-sensitive drum pads, finger drum pads. And we're controlling a variety of beats using this system. So finally, teaching. We've been teaching for this, they're now starting in their 5th semester at Princeton. But we taught, prior to this, we taught 4 semesters of completely different courses every semester. And this is actually the first one, which was a freshman seminar. So we actually started with 15 unsuspecting fresh persons. They had no idea what they're in for, and neither did we. But because of their bravery and lack of, like, they didn't know like we did that they should be really, really scared, because we didn't know what we were doing at the time. But they were totally awesome, and they just went ahead and took this thing to the next level. They just went and tried everything. They weren't afraid to make new pieces, to perform it, and they just carried us through, and their energy just like totally made it happen. And after that, things started falling into place. But they basically came into this in 2005. No prior programming experience with any one of them, but we started teaching them ChucK. And by week 3 and 4, they felt very comfortable. We were actually making drum machines, soundscapes with it, and they were making pieces with it by the end after 10 weeks. And then we have more classes in the spring, the fall, focusing on different aspects of performance, composition, and coding, and also in 2007. And I'll just read you, I actually won't read you, I'm just going to show kind of what one of our students wrote in one of her assignments. She was one of our very finest. So, future work. For ChucK, we're really working on rapid prototyping for music information retrieval, kind of as a focus in ChucK. Not only can you synthesize sounds, but we can analyze them and use them to do, maybe to do machine learning type things, which we can apply to performance or just kind of more, traditional offline kind of type of information retrieval tasks. But we're really interested in kind of the on-the-spot, performance-oriented type of information retrieval. So Rebecca and I and others are working on that at this very moment. And definitely we want to continue investigating new syntaxes and semantics for audio programming. Graphics is coming in ChucK in the form of Gluck or GL and for ChucK. And the big project that's really kind of starting right now is kind of the social audio programming of actually figuring out how to do sound synthesis analysis and performance via code and OnTheFly programming, like kind of online, kind of like a very music-oriented Second Life or World of Warcraft, kind of munched together. But you go in there, you run around, you write code, you make music, and you hear music together that you and others have been making. So that's something we're really interested in. And as far as laptop orchestra is concerned, Dan and Perry and others are going full force at Princeton. And here, I think it's time for the Princeton Laptop Orchestra. We still need a good name. Slork is a pretty good one. SLAM would stand for something like the Stanford Laptop Musical Maelstrom or something. We don't know yet. And another big goal of the Laptop Orchestra, and always has been, is kind of investigate novel classrooms that really sits at the intersection of computer science, music, technology, and not only can you learn technical aspects of music and sound synthesis and computer music, you can then go back and apply immediately into live performance, which is huge and pretty unique and unprecedented. So looking for new interfaces, new instrument, new music, and new people to play them and design them and to program them and to figure out what to do with this. So this is kind of my invitation to everyone to join in any way you'd like. In the end, we'll end with this slight transformation of Lady Lovelace's quote, saying that supposing, for instance, that the engine were susceptible of such expression and adaptation, might not the human compose elaborate and scientific pieces of music of any degree of complexity or extent? And there's the ChucK website and Plork, and hopefully we'll have a Slork at Stanford very soon. And there's a ton of people that we work together on both of these projects, and that's all I have. Thank you very much. Any questions? I don't know if we have time for questions.
Got one over there. Okay.
Put the previous slide back up so I can write down the URL.
Yes.
We got one more, yeah.
A comment rather than a question about like something you mentioned at the beginning that like new technology should change the pitch as well. And actually, two moments I was really astonished was the way how you conduct the orchestra is like a totally different from the traditional orchestra conducting. In a sense, because traditional ones are more controlling the micro timing of the ensemble of people rather than pitch or the other elements, like dynamic expressions. But like still, like yours more like
more high level.
A lot more high level, and then like orchestral language itself may transform into high level, like we did in the computer language. That's why it's so very fascinating. Plus, the way you're like tilting your computers, like it's not supposed to be the normal way of using that computer. Then like it's actually again like extending the use of computer. It's so fun.
Thank you. Yeah, in general, as far as conduction is concerned, it's really the same question of building instruments out of laptops. It's kind of like the line between like composer, performer, it's really blurred. It's like where does it start, where does it end with the laptop and the human? And I think the nice thing in the laptop orchestra is we get to kind of draw the line more or less where we choose. Same with the conducting. Do we want to give more control to the players, or should we have that taken care of by the computer, or vice versa? And the answer to that really depends on the piece, I think, for sure. But thank you for your comments. Yes, Max.
In the orchestras at Princeton, did students supply their own laptops, or did you supply them for them, and what varieties were involved?
Good question. We supplied the laptops for them, we started out with 12-inch Mac and 12-inch PowerBook G4s, the small ones. Then we got a few Intel MacBooks recently. And so we ended up with about 20 laptops right now that we've been swapping in and out of shows. And for our laptop orchestra here, we'll do the same thing. We have funding to actually purchase the laptops in addition to the speakers and to build all the equipment. So it would be the same kind of thing here. It's a good question.
And OS X then for the operating
And
system?
we'll probably get, I'm actually waiting for Apple to confirm or deny this like ultra thin, ultra light 12-inch sub notebook. And if they introduce that, we may very well see quite a few of those. And we're definitely getting a whole bunch of Wii modes and whatever sensors that we can get our hands on into the orchestra as well.
Thanks, Kev.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.